Okay, so back with segment 2. So when I stopped the last segment, we were talking about naming organic compounds. And so I'd given you 3 structures and we worked through how to name them. Now, the next thing I'm going to look at is all the different ways we can draw organic chemistry. So the first thing we want to do is look at expanded structures. This is what we're used to. So here you can see we have carbon in the middle. We draw out our bonds. This is very similar to the electron dot structures we drew back in chapter 5 or 6, chapter 6. And so you can see, we're just extending the carbon chain out here and we're putting those hydrogens on. We left those out when we were practicing naming simply because the drawing gets a little too busy with all the hydrogens on there. And I wanted you to make sure you could see what I was doing and how I was naming and numbering carbons and that kind of stuff. Now, new to organic chemistry is the condensed structure, and I kind of pointed this out in the beginning in segment 1. So what we're going to do is kind of treat the carbon like an umbrella, if you will. So the expanded structure is when we pop the umbrella open, we show all the hydrogens kind of, bursted out. And then, of course, when we pull the umbrella back and we bring the lid down, then all the hydrogens are going to wrap around the carbon that they belong to, if you will. So here you can see these CH3s here became that CH3. And of course there's the propane. Now another way we'll draw, and I don't have it on here, is a stick figure method. I want to make sure you're prepared for this. We use really a lot of shorthand notation in organic chemistry. So for methane, we don't have a structure that would represent that. But once we get to ethane, we do. And what we would do is just draw a line. And the line represents that carbon-carbon bond. And so there's a point on the end of each line. We don't actually draw the points in, we literally just draw a line. And that's going to represent the carbons. So for propane then, it would be 2 lines, but we don't draw it straight because if we do, then you can't really tell that it's 2 lines there and 2 bonds. We want to emphasize that third carbon. And if you remember, when we looked at structure and we looked at methane as a structure, if we put carbon in the middle, we had 1 hydrogen coming straight up, 1 coming out like that, then 1 actually stuck out at us and 1 went behind the board, right? So if you think about it though, these 2 that are in the plane, they make that angle there. And that's what we'll do here. So if I want to look at propane, I'll draw something sort of like that. And now whenever that line segment turns and it has a bend to it, that bend represents a carbon as well. So there's the 3 different ways that we'll draw organic structures. We'll do some more practice with this. This style of nomenclature becomes a lot easier to use when you're looking at bigger molecules. So for some of you, when you start to look at biology and you're looking at DNA and proteins, it's going to be a lot easier to look at structures that are like this versus all those letters and bonds going everywhere. All right, now I need you to be able to switch back and forth between condensed formulas and structural formulas. So when we look at naming problems, especially like on multiple choice questions or even like textbook quiz questions, you might be given condensed structure. And so what you're going to need to be able to do is convert that, right? Trying to name the condensed structure can be a little bit confusing. So what we want to do then is convert our condensed structure into the carbon skeleton. Now we're not going to worry about the hydrogens. We know that carbon has to have 4 bonds, and so we can always count those if we need to make sure we have 4 bonds on each carbon. But what we want to do is be able to convert so that we can see the structure drawn out. So don't get confused by the parentheses here. This is saying we have a methyl group, right? That's all that is. And then we have a 2 down here. So we're just following normal chemistry convention. It's saying we have 2 methyl groups. Now, what it's telling you is the 2 methyl groups are connected to this 3rd carbon here, 2nd carbon in, however you want to look at that. So that this carbon is actually this carbon. And then these are your 2 methyl groups. There's one, and then there's the other. Okay, then it continues on to a CH2, which is this guy. Then another CH2, that's going to be that guy. And then a CH, and that's going to be that guy. And then we end it with 2 methyl groups as well. Well, that's going to be methyl group 1, that's in the parenthesis, then methyl group 2, that's in the parenthesis. Now notice I put the hydrogens on the outside of this carbon here. Don't let that throw you. Remember, the carbon is sort of like a sphere, and those hydrogens are going to be wrapped around. I'm going to put the other one in the back here. They're going to be wrapped around that carbon, and it can rotate around. So keep that in mind. So don't get confused. The reason why we do that is simply because we like to show the backbone. So sometimes we'll throw hydrogens to the outside. In the programs that I use to draw out molecules for different test questions, it is sometimes do that on purpose. And then the other thing you also want to watch out for is a lot of times they'll use a combination of stick and structure. So for instance, like if you have a longer compound, what you might see is something like that, where they'll mix the condensed formula with the structural formula, right? So while you have CH3s on the end, remember that's going to be a CH, a CH2, and a CH2. Okay, so that's really what's going on there. So don't get confused by that. These are all, what we'll do is mix all the different ways we can draw just to make things easier. Now, regardless of how your structure is given to you, you want to get into this backbone form, right? Because that's going to be the easiest way to figure out how to name it. And once you're in that format, now you're ready to name it. And so here we can see now the longest chain is going to be 1, 2, 3, 4, 5, 6 across. So we know that's going to be hexane. And then of course we have two methyl groups, one here and one here, that are not part of that longest chain. And we can go 1, 2, 3, 4, 5, 6. That gives us 2, 5. We can come back the other way. 1, 2, 3, 4, 5. So either way, we end up with 2, 5. And so that's going to be 2, 5 dimethylhexane. All right. So again, the other way to draw is very similar to that structural formula. It's going to be just a single line formula. So carbons are going to be assumed to be present at the end of each line segment. Hydrogen is not shown when bound to carbon. So again, whenever we're looking at more complex molecules, you can see all those hydrogens start to look crazy. So it becomes easier to just draw it as line segments. So now we can see we have 6 carbons, and we know that carbon always has to have 4 bonds. So if I pick any one of these carbons, I can see that I have 1, 2 bonds to 2 other carbons, which means there has to be 2 hydrogens coming off of here, right? No options. So that's what we're seeing when we see that. Now, you'll notice that I moved to the next one, the OHs here. This is going to be one of our functional groups. We'll talk a little bit about that probably in the third segment. But here, when we draw those out, we leave those in. We call those heteroatoms because they're not hydrogen, and they're not carbon. So we call them heteroatoms. Especially when they're functional groups. If they're functional groups, we like to show the functional group even in the line segment drawing, simply because, remember I said, the functional groups are how organic compounds react. And so we like to see those, that way we know what reactions to expect when we see the different combinations. Here's the same thing. We have a nitrogen, our heteroatom in there, and so we'll keep that heteroatom in and however it's connected. So here we can see this is what's going to be called a secondary amine. Now, if it's all straight hydrocarbons, then you notice there's nothing there. So we don't write anything in, we just keep the line segment going. So I know that's going to take some time to get used to that. Make sure you look over it though. Make sure you're practicing these types of things. If you have questions, shoot them off to me and I'll do the best I can to answer some of them. If we need to meet on Zoom maybe and go over some practice, we can. So keep that in mind that you can always reach out to me. Now, the nice thing about line segments is you get the geometric structures. Now, for the line segments, you'll get the geometric structures. And so whenever we see shapes, remember each point would be a carbon. Now, each carbon still has to have 4 bonds. So even though it's making a circle, your overall hydrogen count will be less, but each carbon will still have 2 hydrogens in this situation. Now, when we look at the shape, we know this is a triangle. I have 3 carbons, which means I'm going to call this cyclo because it makes a circle, cycloprop because there's 3, and then ane, cyclopropane. Okay, so cyclopropane. If I have a square, we know a square has 4 points, right? Which would be 4 would be bute, and so we're going to call it cyclobutane. Next one down here we have 5, so it's going to be cyclopentane. And last but not least, 6 will be cyclohexane. Now we won't go any further with that, so you can have 7, 8, 9, 10, 11, 12, multiple membered rings. Realistically, this one's the most stable, which happens to be the cyclohexane, which is 6. Don't worry about that. It's just that's the truth. That one is the most stable of all of the cyclic anes. I guess the best way to put it, the cycloalkanes. All right, so substituents. We've kind of already started working on substituents. We've looked at side chains. And when the side chains are going to be carbons, the carbons are called branches. Okay, so we kind of went over this already. You hopefully got the hang of this. Whenever we have a branch, we end the name in "il." So we have methyl or ethyl or propyl, so forth and so on. Now, when we have branches, what opens up the door is to this other thing called isomers. Now, we've seen this name before, kinda, sorta. If you think back all the way to chapter 3, when we looked at atomic structure, we had not isomers, but when things had different mass numbers, what did we call those? Right, so not isomers, not mers, but isotopes, right? So isotopes. So iso means similar to, so that's what that prefix means. And so when we add branches, we generate these things called isomers. Now, here's what I mean. So we have C4H10. Now, so far what we've seen, what we would most likely do is draw 4 carbons in a row. And of course, 4 in a row is going to be butane. Now, does it have to be 4 in a row? So let's think about that. What if I did 3 in a row? 1, 2, 3. And then instead of making a straight chain, I'll put one in the middle like that. Now that's still 4 carbons, but will I still have 10 hydrogens? And so of course I'll need 3 here so that that carbon has 4 bonds. I'll need a 4th one here. I'll need 3 on this one. And I'll need 3 on this one. So that gives me 3, 6, 9, plus 1 is 10. So I'm still going to meet that formula. So that could be my other structure. Now, both structures then have 4 carbons and 10 hydrogens. Now, when that happens, so we have the same molecular formulas, however, the atoms are connected differently, we call those structural isomers. Now, if you decide to do some of this on your own and you type isomers into Google, be very, very careful because you can get into a whole section of trouble here that's well beyond the scope of what you need to know. So if you're going to go Google this looking for practice problems or something like that, make sure you're using the whole phrase, structural isomers. If not, you're going to get into chirality and left-handed and right-handed and all kinds of silly things, D and L for sugars, and you could really mess up what you need to know and freak yourself out. So make sure you're just doing structural isomers. Now, you can also have a non-carbon substituent. Now, we haven't seen that yet. We've only put branches on, but not all your substituents have to be carbon. Some other common substituents would be the halogens. Now, when we were doing ionic naming and even the non-metal naming before, our binary naming, things like chlorine became chloride, and it doesn't sound nearly as pretty. In organic chemistry, things sound, I don't want to say pleasant almost, but kind of flowery. So for instance, chlorine becomes chloro. Fluorine will become fluoro. And of course, my personal favorite, the reason why I come to work, iodine becomes iodo. Get it? Iodo. But seriously, that's iodo. So iodo, and then of course fluoro. Okay, so again, they have that flowery O rather than a harsh I'd. Now your rules for naming are still looking for the branch, giving the branch the lowest number, and making sure you put things in alphabetical order. So for instance, CCF, right? What does that become? Well, we have 2 carbons in a chain, so our longest chain is 2. That's going to be ethane. The fluorine is connected to the one end, so we're going to count from this side. This is going to be 1, this is going to be 2, and so this becomes 1-fluoroethane. 1-fluoroethane. All right, how about the second one? We have CCC and then an L. And hopefully you came up with 2-chloropropane. All right, this last one's a little tougher. right? It's got a methyl branch on there as well. Whoops, but there's your hint. Make sure you keep the bromine on the main chain. So that pretty much means we're going to have to use that as our longest chain. And so hopefully you came up with 1-bromo, 2-methyl butane, right? So 1-bromo, 2-methyl butane. All right, so before we go on to talk about organic compounds and some of the common factors or general properties, let's do a quick practice problem on isomers, because a typical test question, you'll find one of these in the lab, would be to draw out isomers. So your typical test question might be something like provide names and structures for, let's just say 4 isomers of, I don't know, let's do something 1-bromo, whoops, I don't want to say 1-bromo, I'll just say bromo hexane. Now, for bromohexane, you should be able to come up with way more than 4 isomers, okay? So, in fact, without even moving a carbon, you could almost come up with 4, right? Because if we started out with 1, 2, 3, 4, 5, 6, I could put the bromine here. This would be 1-bromohexane. Right? Then I can move the bromine down. So I could keep the hexane. We'll just put it here. And now I have 2-bromohexane. And again, you can just follow this right down, right? So now we could get 3. Now when we get to 4, you got to be careful though, because then coming from the other side, this would be 1, 2, 3. So we just got 3 of them without even moving a carbon. So you can imagine I can come up with a whole ton of these. So that would simply be 3-bromo. I'm not going to write that whole thing out. Just stop at 3-bromo. Now what I'm going to do is cut a carbon off. That's no big deal. I'm just going to follow this logically. I'm going to do 5 now. 1, 2, 3, 4, and 5. I'm going to put the methyl group there. I'm going to put the bromine here. Now I have 1-bromo, 2-methyl pentane. Then what can I do? Well, I can move the methyl over. Now I got 1-bromo, 3-methyl. Then I can do 1-bromo, 4-methyl. Then I can move the bromine over. So then I've got 2-bromo, 2-methyl, 2-bromo, 3-methyl, 2-bromo, 4-methyl. Then I can move the bromine over one more and get 3-bromo, 2-methyl, 3-bromo, 3-methyl, 3-bromo, 4-methyl. Nope, can't get that one. That becomes 2 again, right? So you got to be careful with that. Just watch out for your symmetry. Make sure you're counting from both sides. Then I can chop another carbon off and make it so that we have a butane chain, right? So now I'm going to put 2 carbons here. Again, I'll put my bromine here. Now I've got 1-bromo, 2,2-dimethyl butane. Then I can move 1 carbon over. Then I have 1-bromo, 2-methyl, right? 2 and 3. So 2,3-dimethyl butane. So forth and so on. So you can just keep chopping carbons off, making the structure, and then moving the bromine around. Now again, on the test, you'll have a question similar to that. Typically, I give you a compound that can have 6+ isomers, and you've got to pick out 4 of them and name them, right? So that's what you're going to need to be able to do for the exam. That's coming up soon, probably next week. And so that will end segment 2. And the last things we have is picking up on organic compounds and then functional groups. So we'll have one more segment and that will wrap up organic chemistry. So stay tuned for that.